All right, so now we're going to talk qualitatively, for the most part, about cyclic alkanes. We spent a lot of time talking about alkanes. We know how to name cyclic alkanes, but let's talk about some of the features that define a cyclic alkane here, specifically focusing on the smaller ones. So first of all, one of the things to remember is, of course, carbon likes to be sp3 hybridized in an alkane or a cyclic alkane, right? No pi bonds. That means that it's going to want a bond angle of 109.5, right? So when we think of all these cyclic structures, of course, when we draw them on paper, they're all in 2D. But let's look at what would happen if indeed they took on a 2D conformation. These bond angles, if it was in a triangle, would have to be 60, a square would be 90, a pentagon 108, so that's pretty close, hexagon 120, heptagon 129, octagon 135, right? So these are outside of what would be that ideal bond angle. So in order to minimize what's called angle strain or anything outside of the ideal 109.5, these shapes are going to deform, these molecules are going to like deform out of just 2 dimensions and take on these other interesting conformations, okay? So let's take a look here. So first of all, let's look at these, what are called heat of combustion. So what does this mean? Well, cyclic alkanes will all follow this formula, CnH2n, right? This will react with oxygen. Cyclic alkanes are found in gasoline. They are really, any alkane is really sort of what powers the world in terms of like petroleum. And of course, the whole kind of problem here is that that releases CO2 as well as H2O. And just look that these ratios are going to stay N and 2N. I'll get N moles of CO2 and N moles of H2O. So because they all have this very similar formula, you can compare the heat that's released when you combust each of these per CH2. Per unit of like CH2, all right? And so what we'll see is cyclopropane, and let's look at this graph here. Cyclopropane is really, really high compared to all of the other ones. And we see that cyclohexane, right? So when the ring is 6 carbons, this would be cyclohexane, is sort of at this minimum here. It's got the lowest heat of combustion. So why do we care about heat of combustions? Well, they really tell you about the stability of your starting molecule, of your original CnH2, because the end is going to be the same for everybody. You're going to get N moles of CO2 and N moles of H2O. So the energy of your starting point is what's going to be leading to those big differences. That means that cyclopropane, so that's this guy here, this would be cyclopropane with 3 carbons, is much, much, much higher energy than cyclohexane. That's why it's releasing so much more heat. So we're going to sort of look at the various factors that lead to cyclopropane, or what would we call it when it's, green is, oh yeah, green's fine. What would we call it when it's 4 carbons, right? This would be cyclobutane. And what do we call it when it's 5 carbons? Cyclopentane. What are the factors that lead to this various stabilities? So first of all, when you have only 3 carbons, so for cyclopropane, this is where we're going to start. When you have only 3 carbons, they have to sit in the same plane. It's kind of impossible not to. Because of that, that means that those bond angles are indeed sitting at 60 degrees. This is very far from the 109.5 degrees ideal. This leads to what we call angle strain. Okay, so angle strain is forcing a bond to be outside of the ideal 109.5. You will get insufficient sigma bond overlap, right? So remember, We want these bonds to overlap so we can form these sigma bonds, but look at how poor that overlap is. In addition, you also have torsional strain. Thinking back to what we were just talking about, it's basically saying that these hydrogens have to adopt an eclipsed conformation at all times. So there is what we call torsional strain in this molecule as well. We can picture that using the Newman projection here. If we took this cyclopropane and light it on its side. If you have a model kit, this is a really good exercise that you can do to show that indeed all of your hydrogens are going to be sitting parallel to one another. They're going to be eclipsed, leading to torsional strain. So cyclopropane is so bad because it has both angle strain and torsional strain, leading to the instability of that compound. When we go to cyclobutane, notice that this little shape here, what's this showing us? So what it's trying to show us is this carbon right here is sort of in the back, and this carbon right here is sitting up front, and then the two middle ones are in between. Okay, and what it's really trying to show you is that cyclobutane is not just a flat square. That's not what it looks like. And what it's really trying to show you is that it will kink itself to avoid some of that unfavorable interaction. It actually still takes on a pretty severe bond angle of 88 degrees, which is of course less than the 109.5. So there is angle strain in this compound. That's part of what leads to its instability. However, the torsional strain is really just not as bad as it was in the cyclopropane. There's only a slight amount of torsional strain because the bond, it kinks itself in such a way that its hydrogens don't have to be fully eclipsed, although they're not fully staggered either. So that's what leads to, it's still pretty unstable, but not as bad as cyclopropane. So then when we get to cyclopentane, so again, let's see if we can make sure that we can understand what this diagram is showing. We're used to just looking at a pentagon. What this is really trying to show us is the fact that that's not an accurate depiction of a conformation of cyclopentane. It doesn't all sit in just two dimensions. In fact, it's going to be kinked kind of as it's shown here. It kinks itself in such a way that the angles are pretty freaking close to the optimal value, right? So they are basically 109.5 degrees. It is still, relative to cyclohexane, there is still a little bit of instability that arises from some torsional strain that happens. If you have a model kit, you can see, but we can also just see in our diagram that they've drawn here, we have these two adjacent parallel hydrogens, right? So those are now in an eclipsed rotational conformation. So that leads to a little bit of torsional strain. If you look at the numbers, actually, you're talking about 5 kilojoules per mole more. Cyclopentane, heptane, octane, nonane, decane are all sitting at about the same value. Okay, none of them quite as stable as the next one we're going to look at here, which is cyclohexane. Okay, now let me just warn y'all now, cyclohexane is something that organic chemistry is obsessed with, especially in this first semester here. We're going to spend a lot of time looking at cyclohexane. Being able to accurately draw it and interpret these structures is going to be a hugely important part of the semester. The ACS just loves cyclohexane, okay? So we're going to sort of beat this particular structure to death. One of the things about cyclohexane is that there is no angle strain, right? It is this ideal, it's sitting at that lowest energy because it has this ideal conformation where it doesn't have to take on any angle strain. It doesn't have to take on any torsional strain either. They're all in these eclipsed conformations. Okay, all those rotational angles are eclipsed. So just like we saw before, we had those fancy drawings depicting sort of like an accurate representation of the conformation of cyclobutane, cyclopentane. This is the famous chair conformation of cyclohexane. We're going to learn how to draw this guy right here. It's going to be hugely important. You can sort of see, trust that those bonds are 109.5, but you can see that there's no torsional strain if we're going to do the Newman projection of this. So we're going to look down these indicated bonds. And this is going to be obviously a little tricky because this is now this friggin' cyclic compound that we're doing Newman structures for. We were just doing it for simpler structures before. So let's make sure that we can follow what's going on here. Again, so let's just take this guy. This is going to be one of my front carbons. It's got this hydrogen sticking up. That is what we call an axial position. You can also have axial down. So these would be, so they're axial up and axial down. 3 axial up hydrogens, 3 axial down hydrogens. Okay, so that's that hydrogen. Let's just follow what's going on here. This is now sticking out. So that's that hydrogen here. This would be what we call an equatorial position. Okay, you have 6 equatorial positions. Each carbon has an axial position and an equatorial position. All the equatorials are pointing out in all different directions. 3 axials point up, 3 axials point down. Okay, if you have a model kit, it will make your life so much easier to just build this thing and look at it. Again, I'm going to sort of focus on what's going on in the chair conformation versus the Newman projection here. So let me just make sure that we can all follow this. I have my back carbon. I have my back carbon. That would be this pink circle here. It's got the axial down hydrogen. That's that guy there, as well as its equatorial hydrogen, that guy there. I guess I can use different green. Okay, so you can see in the Newman projection, the axials are sticking straight up and down, and the equatorials in green are pointed out, right? Now let's just follow along here. We have 2 carbons that are sort of drawn without their hydrogens. This is one of the things that kind of confuse people. We have this orange one here that's represented as that intersection. And the back one here that's sticking up. Is there, okay? And then we are looking down 2 bonds here, right? So they're parallel to one another. So let's just make sure we can figure out where that all is. Again, I have my front carbon. Again, I have my back carbon. So notice how all of my carbons have been accounted for in this structure. I again have my axial hydrogen on the front carbon. That one's pointed up, and I have an axial on the back carbon that's pointed down. I have equatorials on my front carbon, right? Just following that line, it's got to be connected to that front carbon. And I have an equatorial using every color of the rainbow here and equatorial on my back carbon. All right, so I know that's a lot. If you, again, I know I keep saying it, but if you have a 3D model kit, it would really, really help in understanding these structures. But this is sort of how we can look at the chair conformation of cyclohexane as a Newman projection. Just to point out the whole shtick of this, again, being that you can demonstrate that there is absolutely no torsional strain in this molecule. You all have these perfectly eclipsed rotational conformations. There is another known conformation of cyclohexane that is less stable. That's called the boat conformation. This has it doesn't have any angle strain. You can sort of do this yourself with your model kits. You still have these bond angles of 109.5, but now you have significant torsional strain in terms of you no longer have those nice staggered rotational conformations. So one of the most obvious one are what are called the flagpole interactions, and that is steric clashes. So even worse than torsional, right? Torsional just means that you have those eclipsed bonds. Steric clashes are atoms actually sort of bumping into one another. And that occurs at this, like what's called the flagpole position. How do we know that cyclohexane adopts this conformation? Again, it is less stable, but we know that cyclohexane undergoes these what are called chair flips. So you can actually take your model and rotate each one of those bonds and everything will be inverted. Okay, we're gonna sort of diagram this out. There's a whole video dedicated to drawing chairs. So for now, just trust me, okay? The bottom line is we have these carbons that used to be pointed up are now going to be the ones pointed down, and vice versa. The carbons that used to be pointed down are now pointed up. So this is this flip that occurs. And look at this sort of diagram here. Should look familiar, right? We were building our own rotational conformational analysis diagrams using this potential energy plots. This is the same sort of thing where you have the progress from one conformation to another. It's not quite as simple as rotating about a dihedral angle anymore. It actually goes through this sort of weird path here, where first it forms a half chair, then a twisted bow, blah, blah, blah. You don't really have to know the names of these. The bottom line is to know that there's this sort of intricate dance that goes on to go from one chair to another. But we know that this is occurring. You can see that actually in order to do a chair flip, there has to be sort of quite a bit of energy that's overcome, right? So in order to get to that half chair conformation, it needs to have quite a bit of energy that it's going to pull from, you know, the temperature in the environment, for example. But yes, so this is what we're going to focus on next is, again, for now, just know that cyclohexane undergoes these conformational flips going from one chair to another chair, and that chair is the ideal conformation. You have a boat in the middle that doesn't have any angle strain, but does have significant torsional strain. Okay, and so then that was mainly qualitative information on these cyclic alkanes. Now we're going to get into doing some actual chair conformation drawing.